In this session, we are going to deal with the magnetic effects of electric current. We have already dealt what do you mean by electric current, what are its different applications, etc. Isn't it? So, in this chapter, we need to analyze, is there any connection between magnetism and electricity? To do that, we need to analyze it through an experiment. As you can see in the figure, we are going to analyze whether the current and magnetism are related to each other. For that, we need to take a straight thick copper wire and place it between the points X and Y in the electric circuit, as you can see. By the way, what do you mean by current? Current is defined as the rate of flow of charge per unit time, isn't it? That is I equals Q by T. For the flow of charges or the electrons, we need a conductor, isn't it? So, the thick copper wire which we have taken here acts as the conductor. So, we need to analyze whether the current is flowing. Okay. And along with that, we need to analyze whether there is any magnetic field associated with it. We know that in order to detect a magnetic field, we use a compass, isn't it? So, we next place a small compass near to this copper wire. Now, you need to observe the position of the needle. What happens after passing the current? That is what we need to observe. So, now we are going to pass the current through the circuit by inserting the key into the plug. As you can see in the figure, there is a key, there is a resistance, there is an XY point between which we are facing or placing the copper wire, and also a voltage source. So, we are placing the compass near to the copper wire in between X and Y, and we are going to make the circuit on. How? By inserting the key into the plug. Now the circuit is complete, isn't it? Then what will happen? Of course, you will expect a current to flow, isn't it? So now we need to analyze what is the change in position of the compass needle. You can see that the compass needle which we have placed is deflected on passing the electric current through the metallic conductor. So we see that the needle is deflected. What do you infer from this experiment? We can analyze and observe that the electric current through the copper wire has produced a magnetic effect, and thus this magnetic effect affects the needle of the compass, and the compass needle deflects. Thus, we can finalize that the electricity and magnetism are linked to each other. So, the electric current finally contributes to a magnetic field which ultimately results in the needle of the compass to deflect. So, we need to find what are the different terms that are most used in case of magnetism. So, the main thing that when we discuss about magnets come to your mind is that magnets attract, isn't it? But how does this property apply to them? You can see in the figure, there is a magnet given, isn't it? So, one side it is shown as North Pole and on the other side it is shown as South Pole. So, the region around a magnet where we can feel or we can find the force of attraction or repulsion as can be detected is called the magnetic field. And the magnetic field around a magnet is detected using a magnetic compass. As we have already said in the previous experiment, we detected the magnetic field using a magnetic compass, isn't it? And in the magnetic compass, when the needle moves or when there is a deflection, we identify that somewhere the magnetic field is there, isn't it? So, a magnetic field is a region around a magnet, and in that region, the force of attraction or repulsion can be found out. And what do you mean by magnetic field lines? Magnetic field lines are just the field lines around the magnet, isn't it? As you can see in the figure, in the picture, you can see that there is a magnet which is placed, and around them there are certain field lines, isn't it? What is the nature of these field lines? You can see that these magnetic field lines are the paths, isn't it? And they are placed around a magnet. along which the north pole of the magnetic compass needle tends to move. For example, if you place a magnetic compass needle, it will always have a tendency to move towards first to the north pole. So the magnetic field lines, as you can infer from the diagram, they are formed around a magnet, and it can be observed by different ways through different experiments. One of the most common experiment is that if you place a magnet on a sheet of paper and if you sprinkle some iron fillings around it, how does it behave? You will see the magnetic field line patterns around it. It can be also observed by moving the magnetic compasses around the magnet and understanding and verifying how the deflection of the needle happens. Now we need to discuss some of the properties of magnetic field lines or field lines around the magnet. From the figure, you may be able to infer some of the conclusions. What may be that? It's clearly vivid that the magnetic field lines around the bar magnet will emerge at the north pole and it end at or it merge at the south pole. So the magnetic field lines follow a convention that they start from north pole and they end at the south pole. And you can see it clearly that the magnetic field lines are closer at the poles than they are near to the magnet. So the magnetic field lines are always closer at the poles. So the magnetic field lines also do not intersect each other. You can see each of them are independent of each other. None of them overlaps. So the magnetic field lines do not intersect each other. So this particular diagram shows the field lines around a bar magnet. So since we have said there are different experiments to analyze and verify how magnetic field lines are formed around the magnet, a very simple example is as such. First, you need to take a sheet of white paper and you can fix it on a drawing board using some adhesive material or some pins. Okay. And next, you need a bar magnet as a main property. So you need to place a bar magnet in the center of the particular paper. And now you need to have some iron fillings and you need to sprinkle it or distribute it around the bar magnet. And now you have to tap the board gently. What can you see? You will be able to see the very beautiful sight that the iron fillings near the bar magnet arrange or align themselves along the field lines. That is, they form a pattern. How does they form this pattern? That is, you know the magnets have a magnetic property, isn't it? So the magnet will exert some influence in the region surrounding it. That is called as a magnetic field, isn't it? The field that is surrounding the magnet or the place of area where magnet has some influence or can exert a force is called its field, isn't it? So the magnet will exert some influence in the region that surrounds it. So the iron fillings which we placed near to the magnet also will experience a force, isn't it? So this force exerted by the magnet on the iron fillings make it to arrange them in a particular pattern. So you can see that they takes a particular shape like this in which they arrange in a definite pattern or align themselves in a pattern of magnetic field lines that the magnet has a direct effect or force on this iron fillings. So now we need to understand how the magnetic field is created or how it is affected by different types of materials. The first one is the magnetic field due to a current carrying conductor. In the first experiment, we already analyzed it using an experiment, isn't it? So for that, we took a conductor, passed current through it, and besides it, we kept a magnetic compass. And what happened? There was deflection in the needle, and you found out that there was particular current. The current created a magnetic field, and that magnetic field led the needle to deflect. In that case, what did we take? We took a current carrying conductor, isn't it? So here also, it's that what happens. That is, if a magnetic compass is placed near a conductor carrying current or a current carrying conductor. For example, take it as a wire. In case of the experiment that we have already said, we took a copper wire, isn't it? So let it be any conducting wire. Then what do you see? You will see that the needle is deflected. What does it infer or what does it conclude? It concludes that a conductor carrying current has a magnetic field around it. And thus, we finally made the conclusion that magnetism and the current are related to each other. And you have already shown that or seen or through that experiment it was already shown that the deflection of magnetic needle happens. But does it have any connection with the direction of the current? We need to find that. It is found that if the direction of current is from north to south, then the deflection of magnetic needle is towards the east. Then what may be the other case? If the direction of current is from south to north, then the deflection of needle is towards the west. That's what you can infer from the diagram. That is, it is shown north-south as well as the two directions east and west. So, when the current is from north to south, then you can see the deflection of the needle is towards the east. But whereas in the second diagram, you can see the arrow mark, that is, if the direction of current is from south to north, in which there is pointing of arrow, then the deflection of needle is towards the west. So, the magnetic field around a current carrying conductor always appear in the form of concentric circles. This is clearly shown in this particular figure. So, it can be observed that when we pass a current through a conductor, a straight conductor in particular, through a cardboard and spring some of the iron fillings on it, there is something like the concentric circles that you can see in the figure. So, the sprinkling of the iron fillings on a cardboard and passing a current carrying conductor through it, the cardboard, you can see such type of a pattern of concentric circles are being formed. So, the magnetic field due to a current carrying conductor has the properties that we have already discussed. Now, what may be the magnetic field due to a current through a straight conductor? Now, we discuss about a conductor only, isn't it? A current carrying conductor. It can be wire or something else. But what if we specifically say that it is a straight conductor? That is, the current is passed through a straight current carrying conductor. Of course, a magnetic field will be produced around it, isn't it? And if you use the iron fillings to draw the magnetic field lines, you can observe that they also align in concentric circles around the conductor. And the current carrying conductor and the current direction, the magnetic field direction, etc. in this case is found out using a specific rule, and that rule is the right hand thumb rule. That is, we use the right hand and thumb of right hand to specifically find the conclusions. And what this right hand thumb rule says? As the figure insists, if a straight conductor is held in the right hand in such a way that the thumb points along the direction of current and then tips of the fingers or the curl of the fingers show the direction. So, if I have a conductor or a straight conductor in my right hand and I am holding it, so if my thumb points in the direction of current, then the fingers which I have curled around the conductor shows the direction of magnetic field. So, by using the right hand thumb rule, you can find the direction of current and simultaneously the direction of magnetic field. So, the magnetic field due to a current of a straight conductor and a current carrying conductor is already been discussed. What about if the current is through a circular loop? Is there any differences? You can see in the figure there is a circular loop through which current is passing is given, and how the magnetic field there is obtained. When the current is passed through a circular conductor, such as like a loop as you can see in the figure, you know a magnetic field is produced. And the magnetic field produced will be in the form of concentric circles around the conductor. It is clearly shown in the figure. And a difference is that to Towards the center, the arcs of the circles become larger and they appear as almost straight lines. As you can see in this particular figure, towards the center, the arcs of the circle is almost flattened or they are resembling like straight lines. Whereas away from this particular center, they are concentric circles. So along with some concentric circles, towards the center, the arcs of the circles appears as straight lines. How about the current in a solenoid affects the magnetic field? And what do you mean by a solenoid? It is of course a circular coil of wire. And what is its shape? It is clear that it is in the form of a cylinder. So when the current flows through a solenoid, how does it behave? It shows that it behaves pretty like a bar magnet. That it shows properties of a magnet. So the ends of the solenoid will behave just like magnet. What are the two ends of a magnet? The north pole and the south pole. So the magnetic field which is produced by the solenoid will be similar to the magnetic field that is produced by a bar magnet. So what was the peculiarity of the magnetic field lines produced by bar magnet? That will surely apply to this case also. That is, the strength of the magnetic field that is produced will depend on different factors of the solenoid. We have already told that the solenoid is a circular coil, isn't it? And it is in the shape of a cylinder. So the strength of the magnetic field that is created will depend on the strength of current as well as the number of the turns of the coil. So it is clearly shown in the picture that the number of the turns of the coil and even the current can also affect the strength of the magnetic field. So how is the field lines inside the solenoid presented? Are they uniform or are they different in different places? It is shown that the field lines inside the solid are in the form of parallel straight lines. You can see in case of the magnetic field lines that we have already discussed in case of bar magnets, they emerge from north pole and they end at the south pole, isn't it? But what is inside the solenoid happening? Inside the solenoid, is it like the circles or is it like the away from the center? No. When it is inside the solenoid, they have a difference. They behave like parallel straight lines, isn't it? In the center you can see inside the solenoid they are having parallel straight lines. But do they intersect each other? No. We have already seen that one of the main properties of magnetic field lines is that they do not intersect each other. So here also they do not intersect each other, but the field lines inside the solenoid just behaves like that of the bar magnet and they are in the form of parallel straight lines. So what does it indicate? It clearly gives us the result that the magnetic field is same at all points inside the solenoid. But we can say that the field is uniform, isn't it? It is same everywhere inside. So a strong magnetic field produced inside a solenoid can be used in an effective way. How it can be used? It can be used to magnetize a piece of magnetic material like soft iron when it is placed inside the coil. That's what you can see in the picture. A current carrying solenoid is used to magnetize the steel rod inside it. That is, you need to take a solenoid and inside the solenoid you need to keep a steel rod and you can observe what happens. You can see it behaves like an electromagnet, or the strong magnetic field produced inside the solenoid will be used to magnetize the steel rod which we have already kept inside it, isn't it? Just like that you can also keep soft iron inside the coil and that magnet then formed is called as an electromagnet. So electromagnet is of great importance. So what was an electromagnet? As you can see in the figure, if electric current is passed through a wire which is wound around a piece of soft iron, it would also behave like a bar magnet. You can see that we are winding a wire around a piece of soft iron like material and they behaves like a magnet. And such a magnet which is obtained is called as electromagnet. So there are many properties for electromagnet which is used in the commercial applications also. So what is the force on a current carrying conductor in a magnetic field? That is of very much importance. We know that the current has its unit as ampere from ampere, isn't it? So ampere suggested that if a current carrying conductor produces a magnetic field and exerts a force on the magnet, then the magnet should also exert a force on the current carrying conductor, isn't it? So we have already said that magnetism and electric current are linked to each other, isn't it? So if the current carrying conductor exerts a force on the magnet, then the magnet should also exert a force on the current carrying conductor. That is, they act in both directions or they have effect on each of them in a simultaneous manner. So this can be verified by using this particular experiment. In this, as you can see, an aluminum rod is suspended in a horizontal position and it is being suspended using a wire. And where is it suspended? It is suspended between the poles of a horseshoe magnet, isn't it? You can see a horseshoe magnet there and the aluminum rod is suspended horizontally between these poles of the horseshoe magnet. And now what we are going to do is, you can see the setup is being connected to a key as well as a voltage source. That is, the rod is being connected to key as well as the battery, isn't it? So now we are going to pass the current by inserting the key into the plug. And then when the current is passed through the wire, what do you observe? You know, there is an aluminum rod suspended between the poles of the horseshoe magnet and this rod that is suspended is being connected to key as well as the terminals of the battery, isn't it? So once we pass the current through the wire, what does it have the effect on the aluminum rod? Will there be any change? You will observe that the aluminum rod is displaced. And what will happen if I reverse the direction of current? Will there be a difference in the direction of the displacement of the aluminum rod also? You can see that the direction of the displacement of our aluminum rod also reverse if we reverse the direction of the current. And with the inference that the force exerted is maximum if the conductor is perpendicular to the magnetic field. So here you can see the current carrying conductor AB will experience a force perpendicular to its length and magnetic field. So how this displacement happens or what are its different effects? The displacement of the rod in the above activity or experiment clearly states that a force is exerted on the current carrying conductor rod when it is placed in a magnetic field. Here, which is the current carrying conductor that we have used? Here we have used aluminum rod, isn't it? So the force will be exerted on any current carrying conductor when it is placed in a magnetic field. What are the another types or what are the different things that we can infer from this particular activity is that it also gives a hint that the direction of force is reversed when direction of current is also reversed through the conductor. So the direction of force and direction of the current has an effect on each other. Suppose if you change the direction of the field to vertically downwards by interchanging the two poles of the magnet, what can you observe? You will see that the force direction also which act on the current carrying rod gets reversed. And what does it show? It shows that direction of force on the conductor depends on the direction of current as well as direction of magnetic field. So the two things that mainly affects the direction of force is that the direction of current as well as the direction of magnetic field. So this experiment clearly shows that the displacement of rod is largest or the magnitude of force will be the highest when direction of current and the direction of magnetic field are perpendicular to each other. So, the force is greatest or the displacement is of highest when the current and the magnetic field directions are perpendicular to each other. In that case, when the magnetic field and the current is perpendicular to each other, the force is having the maximum magnitude, isn't it? To find such a rule or to find the direction of force in such a case where the direction of magnetic field and direction of current are perpendicular is found out by using the Fleming's left hand rule. For that we use the left hand and we need to find mainly three particular contents, isn't it? That is, there will be a magnetic field, there will be current as well as there will be the motion, isn't it? Or you can say the force, isn't it? In this particular experiment we had these three quantities, that is a magnetic field, a current as well as the force or motion. So, in order to apply this particular rule, how do we find? For that we need to take our left hand. So, what we have to do is, we need to find what is the direction of force, isn't it? So, if we hold the thumb, so we need thumb, the forefinger as well as the middle finger of our left hand. The main criteria is that they should be perpendicular to each other, isn't it? So, this particular thumb holds the direction of motion or force and my forefinger points to the field or the direction of magnetic field and this finger points to the direction of current and they all are perpendicular to each other, isn't it? So, if we hold the thumb, the forefinger and the middle finger of the left hand perpendicular to each other and what are the directions showing? Such that the forefinger points in the direction of the magnetic field, the middle finger points in the direction of current, then the thumb shows the direction of motion or force of the conductor. So, if we know the two quantities, you can find the third one, isn't it? So, the direction of force or motion of a current carrying conductor can be clearly shown by using the Fleming's left hand rule. Motors are used in different appliances for different purposes, isn't it? So, when you hear motor, the first thing that comes to your mind is that a device which is used to pump water from the wells and use it for different purposes like irrigation or for your home purposes, isn't it? But are these electric motors used only there? No, they have a wide range of applications. So, what is basically an electric motor? It is a rotating device and it converts the electrical energy to the mechanical energy. And it is one of the main important components in electric fans, washing machines, the mixers that we use in our homes, the refrigerators, computers, etc. And as we have said, it consists of a rotating device, isn't it? So, from the picture you can see what are the different projects or what are the different components that is present in an electric motor. An electric motor mainly consists of a rectangular coil A, B, C, D as we have shown in the figure. And the peculiarity of this rectangular coil A, B, C, D is that it is made up of an insulated copper wire. So, the coil will be placed as you can see in the figure in between the two poles of a magnetic field, isn't it? One side there is north pole and one side there is south pole of a magnet. So, we are placing the coil in between the two poles of the magnetic field. And you can see that the main aim of this doing is that AB and CD, the two different arms, will be perpendicular to the direction of magnetic field. So, the arms AB and the arm CD will be perpendicular to the direction of the magnetic field. And where do we get this magnetic field? The magnetic field is provided by the magnets we have kept that represent north and south, isn't it? And you can see the coil, the particular coil which is made up of the insulated copper wire. its ends are connected to two halves, that is P and Q of a split ring. And you can see how they are being affected in the inner regions and the outer regions. That is, the inner sides of these half, that is P and Q of the split ring, are insulated and they are attached to an axle. Isn't it? What in case of the outer edges? The external conducting edges of the P and Q of the split rings will touch the two conducting stationary brushes, that is X and Y. So, P and Q are the split rings, X and Y are the brushes. So, the split rings, inner sides and outer sides are connected to different things. The inner side will be connected to the axle and these halves are insulated. And the external conducting edges will be connected to the brushes, that is X and Y. And you can see there is a coil, as we have said, A, B, C, D, isn't it? And how this electric motor works? You can see the current in the coil A, B, C, D comes from the source battery, isn't it? There is a source battery that we have already been connected to the particular experimental setup. Isn't it? So, from the source battery, the current in the coil A, B, C, D enters. And once the current in the coil A, B, C, D enters from the source battery, and through which they enter through the conducting brush S, isn't it? So, through the conducting brush X, they enter the coil A, B, C, D, and they will flow back to the battery through the brush Y. So, one of the main functions of brush X is that they help the current through pass to the coil. And what will be the functioning of the another brush Y? They will help the current to flow back to the battery through that particular brush Y. You can clearly notice that the current in AM, AB and current in the arm CD have a different direction of flowing, isn't it? We have already stated that arm AB and arm CD are perpendicular to the direction of magnetic field, isn't it? Once the current starts flowing from the source battery, what happens? You can see that in the arm AB of the coil, the current flows from A to B. Whereas in the arm CD, what is the direction? It is in the opposite direction, isn't it? It is flowing from C to D. That is, there is an opposite to the direction of current through arm AB. So, in the arm AB and the arm CD, current is flowing, but they flows in opposite directions. And you can also see that the ends of the coils are connected to two halves P and Q, isn't it? And we have already stated how they are connected. So, in one of them, they are insulated inside and the outer edge is being connected to the brushes X and Y. So, we already said that in arm AB and arm CD, the current flows but in opposite direction, isn't it? So, there is a very important rule which is needed to find the direction of force on a current carrying conductor here. It is mainly found using the Fleming's left hand rule. We find that by applying this Fleming's left hand rule, how direction of force on a current carrying conductor is being found. It is found that the force acting on the arm AB will be pushing down, whereas the force acting on the arm CD will be pushing upwards. Thus, the coil and the axle is mounted free so that it turns about the axis and rotates anti-clockwise. At half rotation, you can see the Q will make contact with the brush X and the P will make contact with the brush Y. Therefore, the current in the coil will get reversed and flows along the path DCBA instead of the other path, that is ABCD. So, a device that can reverse the direction of flow of current in a circuit is called a commutator. And which may be the part in this electric motor that act as commutator? It is a split rings which act as commutators. So, the reversal of current will also reverse the direction of force. And where is this direction of force acting? It acts on the two arms AB and CD, isn't it? Thus, the arm AB of the coil that was earlier pushed down is now pushed up. And what happens to the arm CD? The arm CD will be now pushed down instead of the previously pushed up situation. So, the coil and the axle will rotate a half a turn more in the same direction. So, the reversing of current will be repeated at each half rotations. So, each half rotations there will be the reversal of the current direction, and this will give rise to a continuous rotation of the coil and also the axle, and this is how an electric motor works. So, some of the main important points that we need to consider about the commercial motors is that these commercial motors use electromagnet in place of the permanent magnets, and also they have a large number of turns of the conducting wire in the current carrying coil. Since they have a large number of turns of conducting wire, the strength of the field also will be more, isn't it? So, the soft iron core on which this coil is wound along with the coils is called as an armature. So, this will enhance the power of the motor that we use. Yet another important process in case of discussing the magnetic field is electromagnetic induction. It was Michael Faraday who gave his greatest contributions in this field. What does it mean? That is, the motion of a magnet with respect to a coil or change in the magnetic field will induce a potential difference in the coil and produces the induced current. This is called as electromagnetic induction. So, we need to analyze how the motion of a magnet happens with respect to the produced induced current. So, the motion of magnet with respect to a coil, how it leads to the production of the induced current. As you can see in the picture, if a magnet is moved towards or away from the coil of wire, how the galvanometer will behave. If magnet is moved towards or away from the coil of wire connected to a galvanometer, the galvanometer will show deflection. That is, if the magnet is moved towards the coil of wire, what happens? And if the magnet is moved away from the coil of wire, what happens? You can see that the direction and the deflection direction will have a corresponding change. That is, if magnet is moved towards the coil of wire, then the galvanometer is showing a particular deflection. For example, you can see in this particular one, I am moving the magnet first picture towards the coil of wire. What happens? You can see the galvanometer will be deflecting to the left side. And what happens in the other case? If I am moving the magnet away from the coil of wire, now the galvanometer deflection is in the opposite side, or it moves to the needle have a deflection to the right side. So, the current will be induced in the coil due to the motion of the magnet, isn't it? So, this is being clearly vivid from this particular picture. So, change in magnetic field produces the induced current. So, in case of this one, we have taken two coils, that is coil 1 and coil 2. So, we have taken two coils of wire and they are wound around a cylindrical paper rope. And we have to connect one coil to a battery, as you can see, and other coil to a galvanometer. If the current is passed through the first coil, you can see that surprisingly the galvanometer needle shows a deflection, and that is being connected to the second coil. What does it mean? If the current is disconnected in the first one, the needle will move in the opposite direction. This shows that current is induced due to change in magnetic field. So, current is induced in the coil 2 when current in coil 1 is changed. So, a current that induced in the coil 2 is because of the current in the coil 1 which has a change. So, the change in the magnetic field also produces induced current. And we have already seen that Fleming's right hand rule have a great importance. And this gives rise to the direction of induced current being found out. So, using Fleming's right hand rule, we can find the induced current direction. And it is found that the induced current is always to be highest when the direction of motion of coil is to the right angles of the direction of the magnetic field. In such situation, we can use the simpler law. For that, we need the right hand, and it states that if the thumb, forefinger and the middle finger is used and they are held in a perpendicular position, isn't it? So, the thumb will be pointing in the direction of the motion of the conductor, the forefinger will be pointing in the direction of magnetic field, and then the middle finger will show the direction of the induced current. So, this will be showing the movement of the conductor, and my forefinger will be showing the magnetic field direction. Then, if they are held in a perpendicular position, the current induced in the conductor will be shown by my middle finger. So, we should hold it in a perpendicular position. So, the movement of the conductor and the magnetic field is being shown respectively by the thumb as well as the forefinger, and the middle finger will show you the current which is induced in the conductor. Before heading into the next topic, we need to know what you mean by direct and alternating current. So, direct current is also being abbreviated as DC. A current that flows always in one direction is called as a direct current. You can see in the picture how a direct current looks. The current we get from a battery is a direct current. Then what may be the alternating current or AC? A current that reverses the direction periodically as the time moves is called alternating current. Most of the power stations in our country produces alternating current. So, AC will change its direction every 1/100 seconds and its frequency is 50 Hz. You can see that the alternating current shape how it looks. What is the main advantage of AC over DC? One of the main importance of AC is that it can be transmitted over long distances without much energy loss. So, to know about AC and DC is very important when we need to know about electric generators. We all know that whenever there is a need for the current, when there is no supply of electricity in a regular manner, we use an external power source generators, isn't it? So, they are the devices that convert mechanical energy into electrical energy. So, they operate on the principle of electromagnetic induction as we have already seen. They contribute to AC generation as well as DC generation depending on different properties. So, in case of an electric generator, we have a rotating rectangular coil ABCD. So, ABCD is the rectangular coil and it will be placed between the two poles of the permanent magnet as you can see, which is depicted as North Pole and South. So, the two ends of this particular coil ABCD will be connected to two rings, that is R1 and R2. You can see that the inner side of these rings R1 and R2 are insulated, and there is also two brushes B1 and B2. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2. So, the brush B1 will be kept to the ring R1 and brush B2 will be kept to the ring R2. The two rings R1 and R2 are internally attached to the axle, and the axle can be mechanically rotated from outside to rotate the coil which is placed inside the magnetic field. So, the brushes which are present and their outer ends will be connected to the galvanometer. And why galvanometer is used? The galvanometer is used to show the flow of current in the given external circuit. We have already told that axle can be rotated mechanically, isn't it? So, when the axle attached to the two rings that is R1 and R2, is rotated such that the arm AB moves up, then what happens to arm CD? Of course, it will move down, isn't it? Then the magnetic field produced by the permanent magnets will be having a change. Suppose the coil ABCD is rotated clockwise in the arrangement first. Now we have to apply the Fleming's right hand rule to find the induced current which is being shown. And the Fleming's right hand rule, as we have already seen, that the direction of induced current is being shown by the Fleming's right hand rule. That is, my thumb will represent the moment of conductor, my forefinger will represent the direction of magnetic field, and the middle finger will represent the current which is induced in the conductor. So we need to place these three in a perpendicular position. So if I place the moment of conductor as a thumb and magnetic field as my forefinger, then the current induced in the conductor will be shown by my middle finger, isn't it? That was Fleming's right hand rule. So this Fleming's right hand rule is being used here if the ABCD coil is rotated clockwise. So if I apply the Fleming's right hand rule here, we can see that the induced current will be set up in these amps along the direction AB and CD. So the induced current flows in the direction AB, CD. Suppose if there are a large current which is flowing to the coil, this means that the current in the external circuit will be flowing from B2 to B1. So after half a rotation, what happens? The arm CD starts moving and AB moving down. As a result, the directions of the induced current in both the arms change, giving rise to the net induced current in the direction DCBA. So after half a rotation, the arm CD will move up and the AB arm will move down. So the direction of the induced current in the both arms, that is AB and CD, changes, which give rise to the net induced current in the reverse direction, that is DCBA instead of ABCD. So the current in the external circuit now flows from B1 to B2 instead of B2 to B1. So it is obtained that for every half rotation or after every half rotation, the polarity of the current in the respective arms change. So that is an AC current, isn't it? A current which change directions after equal intervals of time is called an alternating current, isn't it? So this device can be called an AC generator. So what about a DC generator? It is a generator which gives a direct current, isn't it? A current which does not change its direction with time. To obtain such a DC generator, a split ring type commutator should be used. With this arrangement, what we get is that one brush will be at all times in contact with the arm which is moving up in the field, while other brush will be all the time in contact with the arm which is moving down in the field. Thus, a unidirectional current will be produced. The generator then is called as a DC generator. We have already dealt with what is AC current and what is DC, that is alternating current and direct current, isn't it? In our houses, we receive current, isn't it? Which category may be that? Is it an AC or DC? In our homes, we receive AC electric power, and what is corresponding frequency or voltage? The AC electric power that we receive in our house are of power 220 volt with a frequency of 50 Hertz. And one of the important devices or component of our domestic electric circuit is the fuse. So we need to know how this fuse acts as a protective one for the appliances of our house. This shows a particular diagram that depicts what are the main components that is present in our domestic electric circuits. As you can see, there is a electricity box fuse, also electricity meter, and also a box that shows distribution containing different switches and the fuses. And it is also showing how much is the volt and hertz that is being supplied in our homes. Along with that, you can see it is being connected to 3 wires. There is an earth wire, live wire and a neutral wire. The live wire is the one which has a voltage of 220 volt, and you can see it is being covered with red insulation. What about the earth wire? The word depicts that it is connected to earth, or it helps in grounding, isn't it? So earth wire has a voltage of 0 potential, which is same as the earth, and it is covered with green insulation. And what about the neutral wire? It has a black insulation. What are the different roles of this live wire, earth wire and neutral wire? That's very important when we understand. And in order to understand that, along with one of the main component, there is a fuse, isn't it? How does a fuse act in our domestic electrical circuits? The fuse is a protective device in an electric circuit. And how does it act? Does it act always? No. It acts in times of overloading. What do you mean by overloading? Overloading is caused when the neutral and the live wire comes in contact. And how does it come in contact? It's when there is some damage to the insulation or some fault in the line. So in terms of overloading, what happens is the current in the circuit will increase, or we say it as a short circuit, isn't it? And it will be very hazardous. And we know the Joule's law of heating, H equals I square RT, that is heat produced is equal to square times the current, the resistance as well as the time. So Joule's heating, that is being applied in the fuse device, which melts the circuit and breaks the flow of current in the circuit. That is, whenever there is an unduly high current, this particular fuse will have an increased temperature and they will melt, and then the circuit will break, and thus the other appliances which are connected to the circuit will be saved. So the fuse will act as a protective device. How? It protects the circuits and appliances by stopping the flow of the unduly high electric current. And how was it placed in case of the domestic electric circuits? You can see that the fuse is placed in series with the device. And the fuse mainly consists of a piece of wire, and it can be made of a metal or an alloy of appropriate melting point. It can be aluminium, copper, lead, iron, etc. So if a current which is larger than the expected or specified value flows to the circuit, then the fuse wire comes into action. Then the temperature of fuse wire will increase, and thus the fuse wire will melt and breaks the circuit, and it protects the other devices which are connected to the domestic electric circuit.